Okay, so it's my great pleasure to introduce the next two speakers. You guys need a microphone?
I would, and I have to warn the audience, I have a strong neurological tremor, so you know, you'll see pointers are not good for me, and I will be tremoring. And we are two, so I'm gonna, we will have to make a change very fast.
So there's a second microphone, if you just let
that's a great idea.
Can I just go?
Yeah. So we don't waste too much time.
Great. Here you go. Okay, so it's my great pleasure to introduce the next two speakers, who are David and Grégoire. And take it away, guys.
So thank you very much. So I'm just going to present some of the work we do as a hat to the presentation of Grégoire, which will be the real meat of it, because he's the real mathematician. I'm just the guy who has intuition, but don't know how to formalize them, on this so-called projective consciousness model we have been working on for several years now. So I'm going to talk about generalities, some stuff like that, and he's going to then do part two of geometry of world model influences behaviors. So I'm going to go very fast. Just how do we frame the problem? We are trying to understand how consciousness can be part of adaptive systems, so as a broader framework of cybernetics, and we use at this point active inference and the free energy principle as a specific framework for modeling. And the type of question we want to address are like, what does the phenomenology of consciousness, or some aspect of the phenomenology of consciousness, taken as a form, literally in the sense of a geometrical form, of information processing, suggest about its role in information access and integration, appraisal and decision making, action programming, and including social cognition. And then, of course, that's the question we have: can mathematical principles capture all this in a unifying manner? It's ambitious, but we're modest. And so some related work. So in a way, in some sense, what we do could be described as a specification of the global workspace hypothesis. You know, we endorse that consciousness acts as a workspace, integrating in a common internal space, multimodal sensory information and perception, memory, imagination in the sense of simulation, for instance, of the future, emotion and motivation emerging from that, and for high-level long-term control and planning with aspects of uncertainty and monitoring reduction, and monitoring or reduction, and all of that all together in a nice framework for the control of adaptive behaviors. And so we start from very general phenomenological postulates, and we may not agree with them, and we have a focus because it's kind of easier to make sense of consciousness in terms of spatial consciousness when you want to do math, in particular geometry, and they are the following. The consciousness is, in the global workspace, is somewhat constituted or involved in internal space that is viewpoint dependent, that is three-dimensional, and that is in perspective. It's like supramodal. It's not just vision, it's broader than your visual field. You have it when you touch something, and all of a sudden you have an inference of the shapes that are in space in relation to some point of view. It entails that space vanishing points at infinity, so a plane at infinity in 3D, and it's also used for perspective taking, for instance, for perception and action. I change my perception at a different perspective, but also internally for imagination and planning. I can imagine myself elsewhere, and for social cognition and empathy when I simulate somebody else's point of view. So if you accept those postulates, then the consequences of that is that the system must be structured by 3D projective geometry, and therefore there must be a group like the projective group that is acting on that space. And the point of view we adopt is somewhat the duality between motion and change of perspective. If I can imagine a change of perspective, somehow it's a model of possible motion for me to adopt after action that new perspective. And of course the idea is that the PGL, the projective group, structure the global internal workspace and acts on information for active inference and more generally for optimization of behavior. So I'm going to go over some basic results, but very fast without entering into the detail. You can talk about it later. You can read the paper. So we, for instance, applied the framework combining free energy minimization and projective geometry, where by free energy minimization, trying to maximize information, is going to calibrate the projective frame. And we could simulate, for instance, perceptual illusion, like the moon illusion in great detail. We could predict non-linear psychophysics functions that then we could kind of fit with similar function obtained in virtual reality experiment. And we applied the framework also to try to understand how the geometry in transforming information can help with appraisal and motivation toward imagination for action programming, and how actually geometrical lensing, if you wish, would affect affective and epistemic values that you can quantify or attractive something is for the system, and then yield drives that through free energy minimization would optimize action. And of course, in the social case, theory of mind, so that when you simulate others' perspective to predict their behavior in order to simulate adaptive and maladaptive behavior. So that's a short video of robots in which we applied those principles. And agent 1 basically is trying to minimize its free energy, and it imagines that the other one doesn't like it. So whenever it projects itself in the mind of the others, it knows that the other likes the cube because he hears his emotion that is at the center, that he knows that it will want to approach, but that if he were to approach, he would get closer to himself, to agent 1. And since it takes into account the free energy that he estimates, the expected free energy that he estimates in the other agent, in the computation of its own free energy, in order to please the other one or not displease him and minimize its own free energy, the only solution he has is to leave. And so basically it's a toy model of social anxiety disorder. And we apply it now in virtual humans. And so for instance, we are interested in theory of mind, and in that case it's a very, very simple situation where an agent, two agents are competing for coffee machine. One is better than the other, and at the same time they want to avoid each other. At least that's what the agent at the bottom believes, but the other agents actually is like being with other people. So they do this kind of optimization in which, for instance, S, the bottom agent, assumes that O, the top agent, has a theory of mind of order 0. That means that it assumes that he will go wherever he pleases with the best machine because it doesn't take into account S. And so then, therefore, it goes S to avoid O goes on the left, but in fact O was doing theory of mind of order 2, so he understood that S was doing theory of mind of order 1, and therefore, since he likes being with people, instead of avoiding it, they meet at the least interesting coffee machine. S sees that the other one is smiling, so it has to revise his prior, and in a second trial, it actually used theory of mind of order 3 in order to be strategically superior to the other agent and avoid it. So basically, all of that using this group acting on information. There's a lot of nitty-gritty details, but you see we can go from perception to social cognition with that. And so now, sorry, I was very speed because I want Grégoire to speak. Now it's Grégoire time, that's the more interesting part.
Hello, and a lot of pressure again. Hello everybody, thanks for the invitation, very happy to be here. So, as you understand, what we're trying to do is basically to try to encode like first-person perspective inside of activation, so inside of like autonomous system. So we want to be able to have a system that doesn't need like a reference frame, an external reference frame, but it only has its own frame, and then when it moves, the object that it sees changes, but it doesn't need to refer to its own frame to be able to see this change. And so why do we want to model this? That's the motivation of psychological, but there's also another motivation, which is we'd like to be able to know what kind of advantage do you get from getting first-person perspective. So to be able to do this, you need to have, like people say that basically if you have a world model in which you can be embodied, where you have your own perspective on it, it has some advantage with respect to this, so everybody has their own theory with respect to the behavior that we'll have. And so the idea is to be able to model this. And why do we want to model this? Because we want to be able to do experiments and also try to see if we can get some like facts that then we can check if they are consistent with what we expect like, psychologically. So to be able to do so, I'll just introduce a bit like the framework that we were considering in the previous experience. So I'm just going to go inside the head of the robots and tell you what's behind. So basically, let's talk about perspective taking. So you have a setting where you have a real world, basically. So the real world is the ambient world where we are all, so you can imagine that there's like a reference frame for everybody. Okay, this is where you define your own configuration, so the configuration that we all have in the space. And then you have one agent. One agent is just a solid. and it has its own frame inside of this big space. And what I'm saying is extremely basic, okay? I'm not going to do like very complicated stuff, but I think that I hope you can all like see why it's an interesting toy model, even if it's not that complex. So you have a solid, which is one reference frame. It's going to move, then it changes its reference frame, okay? And then this object, this robot, this agent, is looking for O, which is an object. So it has beliefs on where O is. And it's going to try to say, okay, so I need to go and explore my environment so that I can try to get more information on where is O. But if I have false beliefs on where is O, I'm going to go towards the green place and say, oh, O is not here, so I'm going to update my beliefs. So this is just basic, like let's say, like POMDPs. So just exploration for an agent, and an agent that is able to predict what's going to happen in the future, predict the consequences of its action. So here the particular point is that the agent, what it does, is that with respect to its reference frame, it's able to take the information that's outside, so like the objects, and bring it back into its internal world model, which has a geometric structure. And so, for example, when it's going to move, as the representation of the external world is associated to its own, like Euclidean frame inside of the space, the object is going to change. And basically, the nature of the geometry you consider inside of the internal world model will deform differently the object that you consider. So depending on the geometry you put on the space inside of the internal world model, like the way you change your frame will change the object in a different manner. And so now that we want to be able to know it, does it change the behavior of the agent? Okay, and it does. Basically, if you take like simple Euclidean geometry, the agent is not going to move. During like if he's driven by curiosity, he won't move. But if you do like projective geometry, he's going to always try to go closer to the object. So that's the key point I want you to convey. And so like any like very like system in robotics, the only way for it to be able to move towards the object is to imagine the consequences of its actions. And so it needs to have a way to predict how its action is going to move. Okay, so now to be a bit more formal, so that's just a general like hand-waving way, but just to convey the idea. So what do we mean by perspectives? We mean groups. What do we mean by world models? We mean homogeneous spaces. So groups acting on spaces, topological spaces. Here we're going to consider measurable spaces. And the only, so this is the general framework I was telling you. So you need, what you need an agent that has beliefs on what it's looking. Here what it's looking is simply the position of the object. It needs to have observation that it can make on where the object is. And the third thing, it needs a generative model. It needs to know the consequences of its actions. So a simple, like the classical way of talking about the generative model, like when it's going to predict what's going to happen in the future. I don't know if you see my yeah. So this x to y, p, y knowing x is the observation. How does so that's x is the internal state. It's what it predicts about the objects that need to model. Then given a configuration inside of a space, it predicts a certain kind of observation. So p, y knowing x is something that is fixed. But what it's going to decide is what kind of action can I do so that I can modify the state of the object, so that I can optimize a certain kind of drive. This is the classical setting where the action changes the state of the space. For us, the action is in fact a change of frame, change of perspective. So how do you model this more precisely? So, sorry, and now what the drive that we consider here is called epistemic value curiosity. It's a particular term that appears in active inference, so it's just one of the terms which allows you to, in fact, choose the way that you're going to choose your actions. So for us, epistemic value has to be redefined for the case where you take perspective, so where a policy of your action is given by a change of perspective, and this gives you, in fact, on small deformation, small movements on your groups, this gives you a flow that you can handle, like they say. So now, as we're in the conference about like categories, so I'll talk about a bit of categories. For people who know it, they're going to find very trivial what I'm saying. I hope for people who know a bit less, they might find it like a way to go into it. So a group is a particular case of a category, like it's one of the simplest. You have one point and all morphisms. Like a good element of the group is a morphism, and they're all invertible. A homogeneous space is a way to represent a group. So basically, you send a group inside of morphisms on a space. So this is a functor, basically. This we've been all talking about the functor, but it's a particular case of function. And the one way of seeing it is you take the affine space. Affine space, you have no single point that is singled out, but you can, if you want to talk about your affine space, you can decide to take a chart, a frame, and then you can say, oh, I have several frames, and I can go from one frame to another one, but you have no single out points. So that's what's important about homogeneous spaces. Okay, and so we were all discussing about like these categories, these structures. How do you do to put like morphisms, so transformation, taking perspective? How do you transform it into a policy from a space X to a space Y? So the easiest way to do it is to consider the probabilistic version of your function, of your transformation, which is simply called the push forward in terms of measure theory, but it's just a way to transform your transformation on space as something that changes distribution. And then from this you can build a kernel, which is simply saying that you have from your function that goes from the space x to y, you can build a transition from x to y. So this is just what I'm considering, and then what we have is, in fact, when we do this, we consider a subcategory of the category of kernels that is structured by, like the Markov kernels given by changes of perspective. You're considering a diagram, which is just a Markov chain that you're taking into this category CG, and then curiosity is a value that you compute on a functor that goes inside of this category, and in fact, optimizing this quantity gives you dynamics on the tangent space of the loop. Okay, so epistemic value, what is it? So maybe some of you are familiar with it, maybe you're not. The key point is, if you have a generative model between two variables, x and y, you can consider what is called mutual information. Mutual information is how correlated are your variables. How far are they from independence? In fact, the better way to see it is to see it as the expectancy of the Kullback distance between the a posteriori and the a priori. It is how much it is surprising to make an observation in mean with respect to your prior. And you're going to try, when you're going to be driven by epistemic value inside of your exploration for curiosity, you're going to try to find places where you're not expected to find the object. So this is exactly what this tells you. So you're going to try to explore spaces that are like to be really sure that your prior is correct, so try to find things that are the most surprising. Okay, and so there's a very simple formulation of this for taking perspective. I told you that the perspective can be written as a transition between x and y, so simply pi of j that goes from x to probability of y, so just a way to choose a policy from x to y, but given by a perspective. And you can build a generative model from it, and then you can directly plug into curiosity by this generative model and do the algorithm, which is you take a prior, you maximize curiosity, you change your perspective, this changes your prior, you do an observation, it changes the prior. Okay, so now we consider two cases. So this I will not go into detail, but just Euclidean projective. And so we have a theorem that you can prove, which is Euclidean, it doesn't move, the agent won't move. Projective, it will always try to get closer to the object. Okay? So this is something you can really prove. I'm not saying the precise details, but you can prove it. So this is like having an interesting result. Why is it interesting? Because it tells you change a bit the way you represent. It will change your drive into the way you will explore. Which is something it's a bit like this idea that we would like to have an integrated, integrate information into space. In the way that you process information into space. So here I'm telling you, if you have different world models, you don't act the same way. And so next step in this is, okay, so now we did this. We did very simple changes of perspective. I didn't tell you how you relate internal state to observations. This is like in a very, it's also taking a perspective, but it's fixed. Now we want to learn it. And why we want to learn it? Because we want to do domain adaptation. Is it possible that having a structure on your internal space is simply a way to be more robust to transformation of the objects that are around you? Is it possible that allowing to have several perspectives on your space allows you, in fact, to be more stable to perspectives you wouldn't have planned? So this is one of the points. And the second, which is more mathematical, it's interesting, but I mean, I don't know if it's that interesting, but at least what you get is that in some way, this trajectory is an invariant, in fact, of your route. So could you build like invariants that are behavioral? I don't really like this. Thank you very much for your attention.
You were very quick. There's ample time for questions. Sorry. Yeah. So thanks about that.
We were used to have people longer, so we were anxious about and with the switch.
Yeah, no, actually, we have 15 minutes including questions left.
Actually, I'd be
yeah, is that actually? What's wrong with that clock? It goes like super fast. Okay, waking up now.
the same way it was going.
Yeah, that's crazy. Yeah. Yeah. Okay, so questions. Yeah, go ahead, please. Yeah.
I'm just curious, like,
maybe not without going into maybe without going into like the full details of the proof or whatever, but like what is it about the geometry being projective that like leads to this difference in the policy that you end up getting close? Like what is what is the essence of like the connection between like the difference in the geometry and like the difference in sort of the agent behavior that you get out?
Okay, so the thing is that so normally if you change perspectives, like your measure entropies won't change because entropy is invariant on the changes of like if you change the way you label your space, it doesn't change. But what is the key ingredient here is that you assume that the certainty that you have on your object is always the same. It's whatever frame you take, the certainty that you will have, so the way you relate the state of the agent, the state of the object, and the observation you will make, is constant. So that makes that if I decide to go for example, for projective geometry, if I decide to go closer to the object, it will seem to be bigger. And so in this case, you get more uncertainty, so you want to get closer. And so this is like as if he was completely stressed out, like I know it's over there, and you're like, no, I'm not sure, I want to go check. You see? Because he's really stressed about this. So that's the idea.
David mentioned theory of mind of order 2, 3. I think I missed what these are, the definition.
You want to answer?
Yeah, I mean, sorry, I went very fast. So basically, it's the theory of mind of order 0 is whenever an agent is pursuing its goal without trying to simulate another agent's mind in order to drive its decision. Theory of mind order 1 is when it's kind of think, oh, the other agent must have theory of mind of order 0. You need to have always n plus 1. So if an agent is in theory of mind order 1, it does entail that it assumes that the other one is in theory of mind order 0. So that means that you are the agent, you think that I'm going to go there because you know or you assume, you infer that I like to go there. But you don't assume that myself I'm making theory of mind about you. My theory of mind order 2 is that you think about what I think you think. So, and then you can go up to n order. Of course, there are limitations in computational capabilities because that's highly recursive. So, the systems that as soon as you go too high, it's implausible in terms of psychology, but on top of that, it's too heavy to do real-time interactions, and you're interested in, we implement things in virtual humans, virtual reality, to try to use agents to kind of make inference about real people in virtual reality as a model of their mind. That will make inference based on their observed behavior to kind of profile people model-based. Yeah. That's what we try to do. Yeah.
So when you have that theory with levels, do you see a really distinct characterization when they're at the same level? Because it sounds like when you have n plus 1 or n minus 1, you'll get sort of a convergence of sense to the behavior, but if they're at the same level, it seems like you might generate some interesting...
Oh, they are mistaken. If, like, for instance, an agent is using a theory of mind of order 1, for instance, it has to assume that the other one is doing 0. But if the other one is actually doing 1, they're going to be mistaken.
How does that reconcile with things like dynamic games, like a homicidal chauffeur, both players are essentially in the same order?
Have to be, what those agents do is that they are actually trying to infer what is the level of theory of mind of the other so that they can have an edge. So, for instance, if I manage to, okay, in this task, what this guy is doing is actually doing theory of mind of order 2. If I want to succeed in my, using the right policy to have the best outcome, I need to be able to jump into theory of mind of order 3.
So, but to clarify my question, I'm interpreting that game as one where they're in the same level because they end up in orbits. And so I'm wondering if the property where they end up in interesting orbits is something I can associate with two players who are playing in the same level.
So what do you mean by orbits here?
So in the homicidal chauffeur, which is a canonical dynamic game, you have basically it's a calculus of variation style problem. You're dynamically optimizing your policy, one to evade and the other to hit. It's like old toy problem for war games, for missile targeting. And the optimal solutions under certain sets of parameters produce orbits, because the further the car type or the pursuer gets from the evader, the easier it is for them to try to turn around and come after them. They have different dynamics, so it produces interesting, like, neither escape it, you can't escape and you can't hit the target. And the reason I brought it up as an example is because, at least in my understanding, that the two players in that game have essentially the same order of mind under this model, And it's weird in part because the results don't resolve. If one of them were higher order than the other, you'd expect them to win the game.
No, yeah, but they can have like partial information, for example.
Yeah,
you can have partial information, but I don't know if that addresses your point, and I'm sorry if I misunderstood it. But again, let's say they have a maximum order of theory of mind they can reach. But then the game for them in terms of inference, as part of the way they predict users' behavior, is to kind of identify what currently the other guy is using as an order of theory of mind to get an edge by being n+1. But then they can be mistaken. And there are also tons of situations where this is undecidable, because the behavioral outcome, is neutral to whether or not you actually were right about the level of theory of mind of the others, or whether or not you were mistaken. So here I just showed, for instance, in the virtual game, one case where it was decidable, which up to the theory of mind of the other three. But actually there are many cases where it's ambiguous. It's intrinsically ambiguous. It's not a problem of machine learning. You won't solve it by learning. It's just the situation is ambiguous.
Slightly lower sort of level question. First off, I really enjoyed the talk. I want to kind of two-part question. One is just I would love just to dig into what exactly is your use of. So you were talking about f-step value and mutual information, or defined as kind of in terms of mutual information. I'd love to understand what kind of work that is actually doing in this. The second part is that mutual information is for example used as a way of explaining the efficacy of certain algorithms in machine learning. For example, sort of cycle-GAN, cycle-consistency, where we're doing transfer learning or sort of cross-domain learning, or transferring from one domain, like horses, to another domain, like zebras. And here, in some sense, you're trying to transfer between spaces and frames, right? I'm just kind of curious if using this underlying projective structure.
So you're referring to ICA, something like this, like what you're saying.
Yeah, it's like ICA.
So here, what you're doing is so the coupling is between x0 and x1. So sorry, start again. So the coupling that you have is between. So you have an MDP, so Markov chain, x0, x1, x2, and then you have some observations. Yep. And what the mutual information you're computing is on xi, yi. So on the state I, an observation I. And the reason why you compute this mutual information is because, in fact, if you just rewrite it, you can see that it's the expectancy of the pullback distance between a posteriori and prior. And so in this case, you don't have but okay.
Any other questions? Sorry, I didn't want to interrupt the question. Just thought this is done. There's another question. Go ahead, please. Yeah.
Yeah, maybe just a super quick question. So first of all, very interesting talk. But one thing that's useful about having theory in mind is gaining information about work. So I was thinking, have you tried to apply these kind of frameworks to always competitive environments where one person might gain information about something in the world after the action of an agent that he sees? Exactly. Then I have a series of clothes in front of me. I see the person next to me that is 1, 2, but he's not finding what we're looking for, so I'm not checking those.
So there's an experiment in this paper, which is there are several experiments. So this the one that we showed is basically to say that it's not that it's a test but it's not to show what we can generate as behavior. There's Salien-An experiment that you can reproduce. So basically, which is exactly what you're saying. One agent can see a box, then the other agent can't, and then you take away the box. So you have a box with something inside, none of them know, and then one doesn't look at the box, you take away the box, and the other knows, you see. Okay, so the other way around, because you put the object, but okay. And this, in fact, works with this framework. We can reproduce the Salien-An. But it's not.
I had a video of that, but he said, no, the other one is more funny, the one that and it's too long to explain, so but I can show you, we have exactly that in
We could have one more question in case anyone else has them. There's one more question.
A bit more about what you said towards the end, which was about the multiple perspectives. I mean, is it possible, does the model that you have allow for at least the possibility to see an advantage to holding more than one perspective at the same time?
Yeah. Okay. So it's at the same time, but not really. So imagine a classification task. So you have a network classification, and you do the formation of the inputs. The thing is, for us, the formation of the input is simply a change of perspective. So because you see a network as a perspective, like our frame. And then this induces a change on the network effect. And then so then you get a space of multiple perspectives. But what you're trying to do when you're trying to learn, basically you're trying to choose one. And you're trying to find a way to go to this perspective with respect to the deformed data you have. That's why I was talking about domain like this.
I wonder if let's see Bob here, but
He's hiding in the back.
I wonder if as like a quantum version of this might allow for a superposition of the network to be in a, yeah, assuming it's instantiation. You know, it's possible to instantiate it in a quantum circuit. Could we get it to be in a superposition, and would that have an advantage?
I would be very happy to hear about it. I mean, for me, I'm unfortunately I'm not that familiar with it. So, I know a bit about quantum, but I never like you.
We get so many we get so many places.
Okay, yeah, so big round of applause again.